If a model has several uncertain inputs and you enter an at-risk function such as risk normal in each of their cells, the uncertain inputs are treated as if they are probabilistically independent. However, quantities in the real world are often correlated to some extent, either positively or negatively. If you know that the uncertain inputs are correlated, and you can measure the extent of their correlation, you should account for this correlation in your model by using at-risk's risk-cormat function. It is usually difficult to gauge how much this actually matters. This depends entirely on the specific model. But there is no excuse for assuming independence when you know it isn't realistic. This video illustrates how to do it. The model shown here assumes that you are going to invest certain percentages of your wealth for some period of time in two stocks and a commodity such as gold. The returns are assumed to be normally distributed with given means and standard deviations. And they are fairly highly correlated. The two stocks tend to change in the same direction, which tends to be the opposite direction from the commodity. For now, focus on columns H to J. The quickest way to build this correlation behavior into the model is to first enter the usual risk normal functions, or whatever distributions you want to use, in the uncertain cells in row 14. Then select these cells, the middle group of green cells in columns H to J, and click the Define Correlations button on the at-risk ribbon. This opens the following dialog box, where you can define a correlation matrix. You give the matrix a name, such as Core Matrix 1. You specify the location for it on the spreadsheet. And you specify the correlations. Actually, only those below the diagonal are required by typing numbers in the boxes. So stocks 1 and 2 are highly positively correlated, and gold is negatively correlated with the two stocks. By the way, if the dialog box doesn't look like this when you open it, you probably forgot to select the input cells first, which is a common mistake. In this case, you can cancel out, select the input cells, and try again. When you click OK, the model changes automatically. It now includes the correlation matrix in columns H to J, and the formulas in columns H to J of row 14 now include the risk cormat functions. For example, the original formula in I14 was the same as in cell D14, just the risk normal. Now it includes a third argument, the risk cormat function. The last two, right here, indicates that this is the second of the three correlated variables. The formulas in H14 and J14 are similar, but they have indexes 1 and 3, meaning that they are the first and third correlated variables. 1 and 3. If you prefer, you can skip the Define Correlations dialog box and type the formulas directly, but this will probably take a little more time and increase the chance of making a mistake. If you do it this way, you should first enter the correlations you want directly into cells, optionally range name the correlation matrix something like Core Matrix 1, and then enter the entire formulas, including risk cormat, in the uncertain cells. Note that there are 3 sets of asset returns in the model, just for comparison. Those on the left are for the case of independent returns, so there is no correlation matrix. Those on the right are for the case where the minus signs have been omitted from the correlations. Now all returns will be positively correlated. I will generate its correlation matrix and its risk cormat functions in the same way as before. plus 0.6, and plus 0.7. Before continuing, it helps to know, at least conceptually, what at-risk does when it runs a simulation with correlated inputs. When it runs, say, 5,000 iterations of a simulation, it first generates 5,000 random values for each of the correlated variables from the specified distributions, in this case, the normal distributions. Then it shuffles or rearranges these sets of 5,000 numbers so that they have the desired correlations. For example, the 5,000 stock 1 and 5,000 stock 2 returns are shuffled in such a way that low values tend to be paired with low values and high values tend to be paired with high values. Now I will run the simulation for 5,000 iterations. Here are the histograms of the portfolio returns. There is independence, there is negative and positive correlations, and there are all positive correlations. The corresponding summary statistics found with at-risk's statistical functions are shown below. They allow you to compare the three cases. First, note that the three mean returns are almost identical. This is no coincidence. Averages aren't affected by the shuffling just described. However, the correlations do affect the variability of the returns. As you can see from the standard deviations and the 5th and 95th percentiles, the portfolio return distribution with positive and negative correlations is less spread out than the distribution with independent returns. And the opposite is true for the model with all positive correlations. It's more spread out. This might not have been immediately apparent from the histograms, but they have different scales on the horizontal axis, which makes them harder to compare. The all positive correlations model is the case of putting all your eggs in one basket, whereas the positive negative correlation model applies to the investor who diversifies. The diversifier has a safer portfolio, whereas the all eggs in one basket investor has more upside potential, but also more downside risk. For each of these models, you can check the actual correlations of the simulated data. To do so, select any cell in a correlation matrix and click the Browse Results button. You see a matrix of scatter plots of the correlated values, along with their sample correlations. Of course, the sample correlation should be close to the correlations you specified. Any differences are the results of sampling error, and these differences will decrease with more iterations. Before concluding this video, I will point out one other feature of at-risk's defined correlations tool. There are some sets of correlations that aren't valid, even though all of their values are between -1 and +1. They are invalid in the sense that no data set could ever have these correlations. I will illustrate one possibility, using the correlations -1, 0.9, and 0.9. When I click this button right here, it checks for matrix consistency. If I say check matrix consistency, I get this dialog telling me that it is not consistent. If I click yes, at-risk will do its best to find values reasonably close to the ones I entered, and in this case it will use the values shown. Actually, at-risk has an option that gives you more control on how the correlations are adjusted, but I won't cover them here. Summarizing, the point of this example is that when it makes realistic sense that uncertain inputs are correlated, either positively or negatively, It is important to build this behavior into the model explicitly with at-risk's risk format function. If you don't, and instead assume independence, the results can be quite misleading. There are some general principles for choosing appropriate probability distributions for uncertain inputs in an at-risk simulation. For example, you can sometimes narrow the choice by assessments such as 1. The quantity must be between 0 and 100. 2. The quantity can have only a few discrete values. Or 3. The distribution of the quantity is skewed to the right. Another approach is to fit possible distributions to historical data on the quantity of interest. Of course, historical data are not always available, but when they are, at-risk distribution fitting tools can be used. These tools automatically rank candidate distributions on their goodness of fit to the data, and then you can make the ultimate choice of the distributions you want to use. As an example, the data set you see here contains 3 years of weekly demands, 156 observations, for a company's product. If a simulation model requires demands in 1 or more future weeks, it is natural to use a probability distribution that fits the historical data well. To find good fits, click the Distribution Fitting drop-down on the At-Risk ribbon and select Fit. Actually, if you already have fit a distribution to the data, it is shown at the bottom of the Distribution Fitting drop-down list, and you can choose it directly. Now, given this resulting dialog box, select the data range and the type of data. The data range should not include the top row that has the variable name. And I'll make this continuous data as opposed to the other possibilities. Next, click the Distributions to Fit tab and select the candidate distributions you want to try. Specifically, once you make some choices about the data in the left side, such as a lower bound of 0, and you're not sure about the upper bound, At-Risk checks all the continuous distributions that satisfy these conditions. If you have never heard of some of these distributions, you can uncheck them, as I will do here. Then you can click Fit. At-Risk fits each of the checked distributions to the data. It ranks them on goodness of fit, and it shows you the results graphically and numerically, as you see here. For these data, the best fits are the gamma, the Weibull, and the log normal, 3 very popular right-skewed distributions of positive quantities. You can see these fits in the graph, where the red curve is the gamma distribution, the green curve is the Weibull, and the purple curve is the log normal. The blue bars represent the histogram of the data. Actually, you can check any of these distributions on the left to see how well they fit the data in the graph. For these data, the triangular and exponential fits are not nearly as good. At-Risk actually ranks the distributions on 5 criteria, the first 2 of which, AIC and BIC, are new to At-Risk 6.0 and are preferred. The other 3 are chi-squared, Anderson-Darling, and Kolmogorov-Smirnov. The rankings can be slightly different depending on the criterion used. For this data set, the gamma, Weibull, and log normal distributions are the top 3 on all of the criteria. At this point, you could enter any of the formulas you see up here into a cell in the worksheet as the demand for some future week. Even easier, you can click the Write to Cell button to enter either of these distributions in a cell of your choice. I will do it for the gamma. Because of the good fits, you can feel comfortable that you have chosen a reasonable probability distribution for demand. Actually, you get some new options, as you see here, in At-Risk 6.0 when you click the Write to Cell button. Specifically, if you select Linked updates each new simulation option, At-risk checks whether the data have changed when you run a simulation. If so, it refits the specific distribution with the new data. For example, if you choose the gamma distribution, it will find updated parameters of the gamma distribution when you start a simulation. In contrast, if you select the Live Updates Whenever Data Changes option, at-risk immediately refits and returns the best distribution whenever the data change. It accomplishes this with the new Risk Fit Distribution function shown here in the dialog box. I'll try this one. Here is the risk fit distribution, and the corresponding cell comment reminds you of the gamma parameters. For example, the alpha parameter is 2.5657. If I now change some data, the parameters will change. As you can see, it's 2.7049 for alpha now. Also, with this cell selected, you can review the fit from the distribution fitting dropdown. There it is. Another change in At-Risk 6.0 is the addition of the Bootstrap option. If you choose this option when fitting a distribution to data, at-risk samples from the distributions being fitted to find distributions of their parameters, including confidence intervals for these parameters. I'll try it. By the way, notice there is the demand data that we already used. I'll just choose it. It remembers the settings. Then Bootstrap, I will run Bootstrap, 1,000 resamples with 95% confidence level. This takes a little bit of time. If you check this option, the next to last button below the fit graph is enabled. If you click it and select parameter confidence intervals, you get a graph like this one. This gives you 95% confidence that the alpha parameter for the gamma fit is between 2.203 and 3.427. There is one other important addition in At-Risk 6.0, the batch fit option. This can be used when you have multiple adjacent columns of related data, as you see here. In this case, batch fit allows you to fit distributions to all of the columns simultaneously. This not only saves time, in contrast to fitting them one at a time, but it also provides the option of estimating correlations between the data variables. The user interface for the batch fit is very similar to the interface for the fit tool, except that there is now a report tab. Again, I will not include the variable labels at the top. I can pick the distributions to fit, just like before. And in the Report tab, I can include correlations. I can place the report in a new workbook, or if I uncheck it, it will be in this workbook. And I can include a detailed report worksheet for each fit. The batch fit results include a fit summary worksheet with the best fitting distribution to each of the data variables: triang, log normal, Weibull, exponential, along with a matrix of estimated correlations. And further information about the fits for each variable appears in separate worksheets. Note that there are formulas in row 9 of the fit summary worksheet, like this one, including the risk format because of the correlations. You could copy these as part of a simulation model that requires values for these 4 variables.